Hello everyone, and welcome back to some more remote learning. In today's video, we're going to do some examples on L'Hopital's rule. And first, we're going to start off with talking about 0 over 0 and infinity over infinity. As we take the limit, we may run into some issues, such as dividing by 0, like in this case. Or what about if you have some function approaching infinity over another function that's approaching infinity? What exactly are those limits? 1, infinity, 0, some other number? We don't know. But that's where we're going to use L'Hopital's rule, which allows us to create an equivalent limit that we can evaluate. So, for L'Hopital's rule, if the limit of f of x over g of x, one function over another function, as x approaches a, if we get 0 over 0 or infinity over infinity, then the limit of f of x over g of x as x approaches a, that same limit is going to be equal to the limit as x approaches a of f prime of x over g prime of x. So our equivalent limit is taking the limit of the derivative of our numerator over the derivative of our denominator as x approaches that same value a. And I just want to note quickly, don't get this confused with doing the quotient rule. We're not doing the quotient rule in this case. We're just taking the derivative of the numerator and writing it over the derivative of the denominator. So let's go ahead and apply this to a function that we already know what the limit is. For example, let's look at the limit of 4x squared minus 5 over 2x squared minus 9x plus 3 as x approaches infinity. We're going to calculate the limit using the methods from our previous lesson, limits at infinity. And remember, for limits at infinity, we use essentially the highest power rule. So my degree in my numerator, the highest degree is x squared, so I'm going to have 4x squared, and my highest degree in my denominator is 2x squared. Because those degrees match, then the limit as x approaches infinity of 4x squared minus 5 over 2x squared minus 9x plus 3, that's going to be equal to, taking those coefficients of those highest degrees, 4 over 2, which is equivalent to 2. So there we have it. We know that our limit of that f of x over g of x as x approaches infinity is equal to 2. But now let's calculate it using L'Hopital's rule. And we can use this because we get infinity over infinity when we try to take the limit. This function goes towards infinity, and this function goes towards infinity. So we can take the derivative of the numerator and put that over the derivative of the denominator. So I'm going to have the limit as x approaches infinity of, what's the derivative of 4x squared minus 5? That's going to be 8x. And then what's the derivative of 2x squared minus 9x plus 3? That's going to be 4x minus 9. Now at this moment, if we took the limit of each, well, the numerator is still going towards infinity, and the denominator is still going towards infinity. So we're in the form of infinity over infinity. What can we do? We can do L'Hopital's rule again. So now I'm going to take the limit as x approaches a, as x approaches infinity, of the derivative of my numerator over the derivative of my denominator. Because this limit is equivalent to our original limit, and because I'm in the form of infinity over infinity, I can make an equivalent limit to this limit. So taking the derivative of the numerator, I get 8. Taking the derivative of the denominator, I will get 4. Now there's not even an x to plug in. What's 8/4? That is 2. So you can see we get the same exact value. That limit is 2. And this example showed how to get that limit, as well as the fact that we can use L'Hopital's rule multiple times. So moving on to example 1, we're going to evaluate the limit using L'Hopital's rule. So for part A, we have the limit as x approaches pi of x minus pi over the sine of x. Let's think about plugging in pi for x. Well, if we plug in pi for x, pi minus pi, that's going to give us 0 in our numerator. And if we plugged pi in our denominator for x, sine of pi, think about that unit circle. The sign of pi is 0. So we get 0 over 0, something we can't evaluate. However, with L'Hopital's rule, we can. So I'm going to have the limit as x approaches pi of, what's the derivative of my numerator? The derivative of x minus pi. Pi is a constant and goes to 0. The derivative of x is just 1. So as of now, I know I'm not going to get a 0 on my numerator, so this looks fairly promising. What's the derivative of sine of x? The derivative of sine of x is a positive cosine of x. So I just created an equivalent limit. So whatever I get for this new limit is what I would have gotten for my original limit. So now can I plug in pi? Yeah, sure, because I have a 1 in my numerator, and when I plug pi into my denominator, the cosine of pi, you can see that's a -1. So I get 1 over -1, which gives me a -1. So my limit in A is -1. Moving on to B, I have 3x squared over e to the x as x approaches infinity. Well, what's that going to be? Plugging infinity in, or taking the limit as my numerator approaches infinity, that goes towards infinity, and my denominator, e to the x as x approaches infinity, also goes towards infinity. So I have infinity over infinity. When we're in this form, what can we do? L'Hopital's rule. So I'm going to have the limit as x approaches infinity of the numerator, that derivative, so that's going to be 6x over my denominator's derivative. The derivative of e to the x is e to the x. Now what happens here? If I attempted to take the limit of my numerator, 6x, that goes towards infinity, and so does that my denominator. So I'm still in the form of infinity over infinity. But that's okay, because what can we do again? L'Hopital's. So we're going to do the limit as x approaches infinity of, what's the derivative of my numerator? 6, and what's the derivative of my denominator? That's still e to the x. So you can see that I have a constant of 6 over something that's approaching infinity. What's that limit? A constant over something that's getting larger and larger and larger. My overall function value gets smaller and smaller and smaller. So the limit as x approaches infinity of 6 over e to the x is going to be 0. And if you're confused as we're taking limits, please refer back and get a quick refresher before continuing on. If you didn't understand the fact that a constant over a function that continues to get larger goes to 0, quickly flip back through those worksheets and do a quick review before continuing on. Next, we're going to talk about other forms. A lot of times we might not get infinity over infinity or 0 over 0 right off the bat, but we need that in order to evaluate the limit. So if we attempt to evaluate the limit and get one of these forms, either 0 times infinity, 1 to the infinity, 0 to the 0, infinity to the 0, or infinity minus infinity, well, we're going to need to manipulate first before we take the derivative and make an equivalent limit. So let's take a look at example A. You can see that x to the third is going to approach infinity, whereas the sine of 1 over x, as x approaches infinity, 1 over x, constant over something that's continuing to get larger, goes towards 0. The sine of 0 is 0. So this is in the form of infinity times 0, or 0 times infinity. And we don't want this form. We want either infinity over infinity or 0 over 0. But think about this. If I have some function that's going towards infinity and some function that's going towards 0, if I was able to create the reciprocal of either of those, 1 over a function going towards infinity goes to 0, and 1 over a function going towards 0 goes to infinity, I'd be able to change this up and get infinity over infinity or 0 over 0. And the one that I think is going to be easiest to manipulate is probably going to be this x cubed, because it takes a little less time to write. But I could move my sine of 1 over x into my denominator if I wanted to. However, I'm going to move x cubed into my denominator. And how do I do that without changing the value? I'm just going to divide by its reciprocal, because dividing by a reciprocal is the same as multiplying by that original. So I'm going to have the limit as x approaches infinity of, my numerator is going to be the sine of 1 over x, and my denominator is going to be 1 over x cubed. You can see that I didn't change the value at all. Dividing by 1 over x cubed is still the same as multiplying by x cubed. I just wanted to put something in a denominator. Now when I take the limit of this, we know the sine of 1 over x goes towards 0, and 1 over a function approaching infinity also goes to 0. So both my numerator and my denominator are approaching 0. Now I can utilize L'Hopital's rule. So I'm going to take the derivative of my numerator and put it over the derivative of my denominator. So I'm going to have the limit as x approaches infinity of, what's the derivative of sine of x? Good thing we know the chain rule, because that's going to be applied. The derivative of sine of some function is cosine of that function times the derivative of the function inside. So this is going to be the cosine of 1 over x times, what's the derivative of 1 over x? That's kind of like x to the negative 1. Taking the derivative of that is negative 1x to the negative 2. Dropping that exponent down in front and decreasing it by 1. So this is negative 1 over x squared. So that gets multiplied by negative 1 over x squared. And then I'm going to divide by my derivative of my denominator. What's the derivative of 1 over x cubed? It may be easier to think of as x to the negative 3. X to the negative 3, bring that exponent down in front, and then decrease it by 1. So this is going to be negative 3 x to the negative 4th, or negative 3 all over x to the 4th. Now looking at this, it seems a little messy. Let's see if I can simplify it down. First off, my negative will cancel out with my negative, so I'm still having a positive over a positive. And as opposed to dividing by 3 over x to the 4th, let's multiply by that reciprocal. So multiply by x to the 4th over 3. Doing that, you'll see that my x squared in my denominator within my numerator is going to completely cancel out. So I'm going to be left with the limit as x approaches infinity. So I'm going to get the cosine of 1 over x, and that's going to be multiplied by, because I flipped that fraction up, and my x squared canceled out with 2 of my x's in my numerator. I'll be left with x squared over 3. So this is multiplied by x squared over 3. And look what happens. As x approaches infinity, cosine of 1 over x, because 1 over x approaches 0, cosine of 0 approaches 1, and then x squared over 3 approaches infinity. So this limit, we know, approaches infinity. Let's continue on to the next problem. Moving on to part B, let's think about taking the limit as x approaches infinity. 1 plus 4 over x squared. 4 over x squared as x approaches infinity goes to 0. So this is going to be equivalent to 1, because the inside of my parentheses is approaching 1, and then my exponent is heading towards infinity. 1 to the infinity is one of those forms. So let's see if we can manipulate this. Remember, we want to try to get infinity over infinity or 0 over 0, and we have a little bit of an issue here because we have this exponent up in here. And obviously there's no way to distribute it in because there's addition, so distributing it in won't help us simplify it down. But how can I get rid of an exponent? Taking the L in, the natural log. So if I have the limit as x approaches infinity of the natural log of 1 plus 4 over x squared, all raised to the 2x, when I take the natural log of this, my exponent can be brought down in front. So I'll have 2x times the ln of 1 plus 4 over x squared. But wait a second. What I just did is I just introduced the natural log into my limit. So now I no longer have an equivalent limit because I completely changed the value of the function. However, think about the inverse of the ln. That's going to be e. So in order to reverse what I just did, my limit, if I get L for this, then my limit of my original, because I introduced the L in, if this limit is equivalent to L, well, my original limit, I'm going to erase this 1 to infinity right here, and I'll write it on the side so you remember what form we were in. But my original limit is going to be equal to e to the L. So whatever I get for this limit, now that I've introduced an L in, my final answer is going to be e to the L. So let's figure out L in order to figure out our overall limit. If we're looking at this currently, if I'm taking the limit as x approaches infinity, 2x approaches infinity, and remember, inside of those parentheses is approaching 1. The ln of 1, that approaches 0. So currently, I'm in the form of infinity times 0, or 0 times infinity. So when I'm in this form, all I have to do is move one of those functions into my denominator as its reciprocal. That way I don't change the value. And because this ln gets a little messy, let's go ahead and do this simpler function to x. So I'm going to take the limit as x approaches infinity of leaving ln of 1 plus 4 over x squared as is. I'm going to divide by the reciprocal of 2x. So that's 1 over 2x. So you can see I didn't change the value of my problem at all. This is still all equivalent to L. However, now I'm going to get, plugging infinity in, my numerator goes to 0 and my denominator also goes to 0. So because I have 0 over 0, what can I use? L'Hopital's rule. So I'm going to take the derivative of my numerator and put that over the derivative of my denominator. So L is going to be equal to the limit as x approaches infinity of the derivative of my numerator. Remembering that chain rule, it's going to be 1 all over 1 plus 4 over x squared. And then I have to multiply by the derivative of the inside, the derivative of that 1 plus 4 over x squared, since I already took care of that ln function's derivative. That's going to be taking the derivative of 4 times x to the negative 2, which comes out to be negative 8x to the negative 3, or negative 8 over x cubed. So my numerator derivative is taken care of. Now I just need to do the derivative of my denominator. The derivative of 1 over 2x is the same as 1/2 times x to the negative 1, bringing that negative 1 down in front, and then decreasing it by 1, I'll get negative 1/2 x to the negative 2, which is negative 1 over 2x squared. Now let's simplify this down. Notice that my negative will cancel out with my negative, and as opposed to dividing by 1 over 2x squared, I'll multiply by its reciprocal. So I'll bring that back up into the numerator. So this will be 2x squared all over 1. And let's see what happens. I'm going to have L equal to the limit as x approaches infinity of 1 times 8 times 2x squared is 16x squared, but I'm dividing that by x cubed, so that's going to be 16 over x, and then that's multiplied by 1 over 1 plus 4 over x squared. This simplifies down to the limit as x approaches infinity of 16 all over x plus 4x over x squared. You can see that I just distributed this x to the 1 and to the 4 over x squared to give me x plus 4x over x squared. My x will cancel out with the x squared to leave me with 4 over x. Taking the limit of this as x approaches infinity, I have a constant of 16 over, what happens with this is x goes to infinity, and 4 over x goes to 0. Infinity plus 0 is going towards infinity. So if I have a constant over my function that's approaching infinity, well, that all is going to go to 0. And remember, that was equal to L. So if 0 is equal to L, then for my original limit, that's equivalent to e to the L, which is e to the 0, and that's equal to 1. So my limit of 1 plus 4 over x squared, all raised to the power of 2x, is equal to 1. Let's move on to part C. In part C, what do we have? As y approaches 0, sine of 0 is 0, and y goes to 0. So this is in the form of 0 to the 0. So we got to somehow manipulate this to get either infinity over infinity or 0 over 0. And that exponent is giving us issues, so let's bring it down in front. And the way we do that is by taking the L in. But remember, making a note that this is 0 to the 0, if we take the L in, then our limit is going to be equal to e to the L, because L is going to equal the limit as y approaches 0 of the ln of sine of y raised to the y, which, taking the ln of that function, allows me to bring my y down in front. So I'm going to have y times the ln of sine of y. Now think about it. Remember, sine of y as y approached infinity went towards 0. The ln of 0 goes towards infinity, assuming that we're approaching from the right, because remember, negative numbers are not in our domain for ln, so we're only going to be able to approach 0 from the right. And then y, as we approach 0, goes to 0. So now we have 0 times infinity. We've dealt with this a couple times before. All we have to do is move one of those functions into the denominator. And how I go about doing that is by writing it as a reciprocal in the denominator. So this L is going to be equal to the limit as y approaches 0 from the right of the ln of sine of y all over 1 over y. Now we're going to have infinity over infinity. As we approach 0, the ln of 0, that's approaching negative infinity over infinity. It's still some infinity over infinity. So what we're going to do is take the derivative. So we're going to get that L is equal to the limit as y approaches 0 from the right of 1 over sine of y times, what's the derivative of sine of y? That's going to be cosine of y, all over, what's the derivative of 1 over y? That's like y to the negative 1, which becomes negative 1 over y squared. So now let's see what happens. L is going to equal the limit as y approaches 0 from the right of cosine of y over sine of y. And then I'm going to multiply by the reciprocal of my denominator in order to move it up into the numerator, and that's multiplied by a negative y squared. So let's think about what's happening. As we approach 0, cosine of 0, that's 1, but we still have 0 because negative y squared as y approaches 0 goes to 0. And then sine of y as y approaches 0 goes to 0. So we technically have 0 over 0. So what are we going to have to do? We're going to have to take the derivative of the numerator and put that over the derivative of the denominator. So now I'm going to have that L is equal to the limit as y approaches 0 of, what's the derivative of cosine of y times negative y squared? That's going to be a little bit of the product rule. And I'll just go ahead and extend this out so you can see my numerator. So cosine of y, I'll do first, times the derivative of the second, so that's times a negative 2y, plus second, which is going to be negative y squared, times the derivative of the first. The derivative of cosine is negative sine of y, and that's all over the derivative of sine of y, which becomes cosine of y. And now we'll be able to evaluate this limit, because as I plug 0 in for y, cosine of y goes to 1, but then it's multiplied by 0, plus negative y squared, that's going towards 0. So this numerator is all going towards 0 over cosine of y as y approaches 0 is going to be 1. So 0 over 1 is going to be 0. But remember, that's not my limit, that's what L is, and I'm going to plug in 0 for L. So I'm going to get e to the 0, which equals 1. So the limit of sine of y to the y as y approaches 0 equals 1. Moving on to d, what do we have in this case? We're going to have infinity to the 0. So this is in the form of infinity to the 0. Again, we don't want that exponent where it is, so we're going to have to take the ln. So this is going to become e to the l, where l is equal to the limit as x approaches infinity of 1 over x, bringing that exponent down, because we're taking the ln of x squared plus 3x minus 4. And the nice thing about bringing that exponent down is, as opposed to writing it as 1 over x times the ln of x squared plus 3x minus 4, I'm going to write it as ln of x squared plus 3x minus 4 all over x. And we can see here, we're going to have infinity over infinity. So let's get started using L'Hopital's. We'll take the limit as x approaches infinity of the derivative of my numerator is 1 over x squared plus 3x minus 4, all multiplied by that derivative of x squared plus 3x minus 4, which is 2x plus 3. And that's all divided by the derivative of my denominator, which is 1. So what I have here is I'm going to have the limit as x approaches infinity of 2x plus 3 all over x squared plus 3x minus 4. What happens here? Highest power rule, right? A degree of 2 grows faster than a degree of 1. So, because my denominator is growing faster, this is going to approach 0. And that was, again, L. So I get e to the 0, because 0 is L, which also gives me 1. And then lastly on my worksheet, I'm going to go over e. And I know up above, whenever we took the ln, a lot of times we got e to the 0, but I want to let you know that not every time will your L equal 0. It all depends on your function. So don't always assume that because you're taking the ln and you're using the limit that you're eventually going to get that original limit equivalent to e to the 0, because that's not always the case. So just be careful and make sure you're going through the steps to see what the original limit is equivalent to, because sometimes that L isn't going to be 0. Let's move on to part E though, where in this case you can see that I have infinity minus infinity. And why this one's important is because I have y cubed and then I have the cube root of y to the 9th minus y squared. If I was to cover this up, look, y cubed minus y cubed, that would equal 0. But just looking at this looks like it's going to be a smaller function than this because I'm subtracting a xy squared within that radical. But I don't know if infinity minus infinity is going to give me 0 or if it's going to give me something else. Or maybe I'm going to be approaching negative infinity or infinity. I just don't know. So what we're going to do is we're going to manipulate this, because what do we want? We want infinity over infinity or 0 over 0. Now in order to simplify this down so that I can get infinity over infinity or 0 over 0, I need some multiplication between my terms. And the way I can get there is if I pull a common term out. And that term that I want to pull out is a y cubed. But in order to pull out a y cubed, I need to have a y cubed available in each of my terms, which with a little bit of manipulation I do. So rewriting y cubed, because that one I can easily pull out, how do I get a y cubed out of this? Well, that's if I have a y to the 9th multiplied by everything. So I'm going to have the cube root of, I want y to the 9th multiplied by everything. So that means that this first term is 1. Y to the 9th times 1 gives me y to the 9th. And I'm going to be subtracting, pulling a y to the 9th out of 8y squared is going to leave me with 8 over y to the 7th. And you can see, again, if I distributed that y to the 9th in, I'd have y to the 9th minus 8y to the 9th over y to the 7th, which is 8y squared. But doing this allows me to rewrite my limit as y cubed minus, because my y to the 9th is multiplied, I can pull that cube root of y to the 9th out. So that would be y to the 3rd times the cube root of 1 minus 8 over y to the 7th. So now I have y cubed and y cubed. I can pull y cubed out of both my terms. So this is going to be the limit as y approaches infinity of y cubed, all multiplied by 1 minus the cube root of 1 minus 8 all over y to the 7th. And why I did this is look what I have now. If I'm approaching infinity, y cubed approaches infinity, and 1 minus the cube root of 1 minus 8 over y to the 7th, well, if I'm approaching infinity, 8 over y to the 7th goes towards 0, and 1 minus the cube root of 1 is going to be 1 minus 1, which gives me 0. This is going to be infinity times 0. So all I have to do is move one of those terms into the denominator. What I'm going to move is that y cubed. So because I got infinity over 0, moving that y cubed, I'm going to have the limit as y approaches infinity of 1 minus the cube root, which I'm just going to write as 1 minus 8 over y to the 7th, all to the 1/3, and that's all over 1 over y to the 3rd. You can see I didn't change that value, I just moved that y cubed into the denominator. Now, when I did that, as I approach infinity, the numerator is approaching 0, and my denominator is also approaching 0. 0 over 0, let's perform L'Hopital's rule. So I'm going to get the limit as y approaches infinity of the derivative of my numerator. Well, for me, this 1 goes to 0, but then I'm going to have to do a little bit of chain rule. So I'm going to bring my 1/3 down in front. That'll get multiplied by 1 minus 8 over y to the 7th, all raised to the negative 2/3 when I decrease that exponent, but then I have to multiply by the derivative of the inside, which this 1 goes towards 0, so the derivative of negative 8 over y to the 7th. What's the derivative of negative 8 y to the negative 7th? That's going to be a positive 56 y to the negative 8. So 56 over y to the 8th. That's the derivative of my numerator. The derivative of my denominator, 1 over y cubed, y to the negative 3. Taking that derivative is negative 3 y to the negative 2, or negative 3 over y squared. So now what I'm going to have to do is I'm going to have to simplify this and see if I can evaluate my limit. So I'm going to have the limit as y approaches infinity of, if you can envision flipping that negative 3 over y squared up into the numerator, that's going to be a negative y squared over 3. My y squared will completely cancel out, and I'll be left with y to the 6th. So, because I still have this negative, I'm going to take the limit as y approaches infinity of negative 56 all over 3 times 3 is 9, and I still have this y to the 6th, so I have 9 y to the 6th all multiplied by 1 minus 8 over y to the 7th raised to the positive 2/3, taking this term and writing it as a positive exponent in my denominator. So what happens when I take the limit as y approaches infinity? Well, my numerator is a constant. This term goes to 0, so I'll have 1 times a function going towards infinity. So if I have a constant over a function that's approaching infinity, this is going to go to 0. So my limit, that original, y cubed minus the cube root of y to the 9th minus 8y squared, that is all equal to 0. And with that, we wrap up this L'Hopital's worksheet. I know some of these problems were pretty in-depth, but as long as you remember that you need to get into the form of infinity over infinity or 0 over 0 to utilize the rule, then you're all set. But until then, it's just a little bit of algebraic manipulation. So keep on doing practice problems until moving on to the next problem. But until then, good luck with your online learning.